Monday. All right, ladies and gentlemen, this class recording has started. So, on Monday of last week, we started in on our study of mechanics. And we said mechanics was the study of motion. And in the course of studying mechanics and studying the motion of an object, we said that there are 4 questions that we want to answer in order to accurately or fully describe the motion of an object. And we've talked about a couple of those questions so far, 2 of them to be specific. So what was the first question that we talked about on Monday that we want to answer? So go ahead. Where is the object? And we said that question gets answered by a single word that we call the position, right? And position is where an object is relative to the reference point. And we talked about then if we change the position, we can talk about the displacement or the distance traveled, depending on what we want to talk about. Okay? The second question that we want to answer in order to accurately describe the motion of an object is what? What is the object doing right now? And Billy, we talked about 2 words that sort of answer that question. What are the 2 words that describe what an object is doing? Okay, someone else want to help him? What are the 2 words that describe what an object is doing? Julia, go ahead. Those go along with one of those words, correct? Speed and velocity, right? And we talked about that speed and velocity are similar, but they are different, right? In that velocity is a vector quantity, and Julia, that means that it has to tell us magnitude and direction, right? Not only how fast an object is going, but which way is it going, right? So, we talked about where an object is, we talked about what it's doing. Put those 2 things together, and we end up with summarizing those things in a graphical form. So, here is a picture of 2 swimmers and a graph that goes along with those 2 swimmers to measure their motion. And up at the top it says that these are position versus time graphs. So, in hopefully kind of a duh moment, if we have a position versus time graph, it should tell us 2 things, right? What should it tell us? Position and time, right? So it should answer 2 questions for us, right? It should answer where and when, right? So it should tell us where an object is at a certain point in time. The next slide that you have on your sheet, which is this slide right here, has 4 questions that relate to the motion of those swimmers and the graph that is on the previous slide. I would like you to take 1 minute and talk to the person next to you and answer those 4 questions based on this graph. I will leave this graph up on the board so you can use it, and so you don't have to, that graph that you have on your slide is kind of small, but talk to the person next to you, 1 minute, answer those 4 questions based off of this graph. Go. So let's talk about these 4 questions. Question number 1, what is the position of swimmer number 1 at 20 seconds? How many of us wrote this? How many of us wrote that? Alright. So, what? Okay, so, well, no. So, alright. So we said that position tells us where, right? So we look on the graph and we find the 20-second mark, right? And then we come up here and it tells us that swimmer 1 was at 40 meters, okay? But we also said that position is a vector quantity, right? And Julia, that means what? If it's a vector quantity? Magnitude and direction, right? So it's 40 meters away from the starting point, but we should specify whether it's 40 meters this way or 40 meters that way. And that's where the positive sign comes in. Okay? Technically, it could be 40 meters behind the starting point. The swimmer wouldn't be in the water, but they could be 40 meters in the other direction. So we want to try and specify that one way or the other. Okay? That was just for the putting the E was how we specified the direction for the guy at the gas station, right? Okay? That here, if we talk about this graph being an x-axis and a y-axis, right? Usually on the y-axis, we call this direction positive, right? And then that direction negative. So this would be on the positive side. We don't necessarily know whether that's east, west, north, or south, because it doesn't really tell us, but it is one direction versus backwards. Okay. All right, number 2. How far ahead of swimmer number 2 is swimmer number 1 after 20 seconds? 20 meters? Did I do that right? Yeah, okay. Yeah. In that case, we don't really need a positive or negative because it's just asking us for a distance. How far? Right? So we don't really need that positive, negative. It's just a distance there. Okay? Number 3, what is the displacement? We said that in order to calculate the displacement of something, we have to know 2 things, right? What do we have to know? Initial position and final position, right? That displacement is x final minus x initial. Now in this case, right, because of the graph that we're dealing with, we're not exactly looking at the x-axis, we're looking at the y-axis, because that's where the position is, right? So here's 40 seconds, that's 80. Here's 10 seconds, only 20 meters, so the displacement here would be positive 60. And in that case, it's important to make sure that we know the positive. Okay? Good with those 3? All right, last one. Which swimmer's faster and how can you tell? So, which swimmer's faster? There. How do you know? Okay, that's true, right? What is that steeper slope telling us according to the information on this graph? It goes more meters in the same amount of time, right? Both of these swimmers swam for 50 seconds, but swimmer 1 went 100 meters, where swimmer 2 only went 50, right? So they can go more, swimmer 1 goes more meters, but in the same amount of time, right? All right, real quick, like again, hopefully just kind of a duh sort of thing, right? Some information about position time graphs. So because they are position time graphs, they have to tell us 2 things, right? Billy, what are the 2 things they have to tell us? What are the 2 things a position time graph has to tell us? No. What are the 2 things a position time graph has to tell us? Where and when, right? So it details the location of an object at a specified moment in time. When we are setting up a position versus time graph, time goes on the x-axis, position goes on the y-axis. I know when I give you slides like this, the spaces aren't really that big to write. I apologize, but there's lots of pictures on today's graph, or today's notes, so I wanted to make sure you had all those pictures. Okay, good there. All right, Sarah, when I asked the question before, which swimmer was faster, you told me swimmer 1, and your original reason was the slope was steeper. So let's talk about slope, right? Slope is a concept that you got introduced to, I don't know what, back in pre-algebra or something, right? Back in 6th grade or whenever you took pre-algebra, okay? Okay? How do we define the slope of a line? I heard it. There's two people talk at the same time, right? How do we define the slope of a line? Rise over run, right? Okay? Now, mathematically, we summarize the idea of rise over run as delta y over delta x. We just talked about that delta means what? In any capacity, delta means, what does the delta mean? Change, right? How much does it change on the y-axis? How much does it change on the x-axis? Now, in math class, rise over run are just two numbers on the y-axis and on the x-axis. But on this graph specifically, the y-axis means something. What is the y-axis telling us on this graph? Distance. And we learned that the change in the distance, right, or position, we call the displacement. So we got distance on the y-axis, and then what's on the x-axis of this graph? Time. So the slope of this graph is a ratio between displacement and time. Back on Tuesday, we gave the ratio between displacement and time a name. Tommy, do you have it there? Or, well, displacement in time is velocity. Distance in time would be speed, right? So, even though this graph doesn't tell us velocity, because of the ratio between the two things it does tell us, we can tell about the velocity, right? So, if we even look at it from a unit standpoint, what unit are we measuring on the rise axis? Meters. What unit are we measuring on the run axis? Meters over seconds is the unit that we use for what? Speed or velocity, right? The slope on a position versus time graph tells us the velocity of an object. So, on your sheet that I gave you today, the slide that is in the middle of the bottom row on the first page, there's like 5 or 6 questions there. We're going to answer those 5 or 6 questions over the next couple slides, okay? So the first one, right, what do the units of the slope on a position versus time graph tell us? Meters over seconds, and that means slope tells us velocity. Okay? Good there. Good with those ideas? Okay. The bottom right of the front side of that sheet I gave you today has 4 graphs. We are going to look at those 4 graphs over the next 4 slides and talk about them in more detail. Here is the first graph. And up at the top, it says, describe the motion of this object. 30 seconds. Talk to the person next to you. Describe the motion of this object. Go. Let's discuss. So, how does this object start off in this picture? What's staying the same? The distance is staying the same. The time is not staying the same, right? Time is the x-axis, right? So the time is increasing, right? But the distance is staying the same. That would look like what? What does it look like when something's distance isn't changing? It's staying still, right? It's just sitting there, okay? But then what happens after a little bit? The distance starts increasing. How is the distance increasing? It's going up steadily, right? It is steadily increasing distance. What other word could we use or description could we use? Julia, go ahead. Constant. Constant. What do we talk about the rate at which distance is gained? Or the rate of displacement? It's a steady or constant velocity. All right? Then what happens at the end of this? It stops again. Is it in the same spot that it was at the beginning? No, but it is stopped, right? So, two things we get out of this first graph, right? Straight lines on position versus time graphs are objects moving with a constant velocity, because straight lines have constant slope. Right? Does that sound familiar from math class, hopefully? Okay? This is true unless what is true about the slope? There's two lines on this graph where we might amend this statement, right? What's the slope of a horizontal line? 0, right? What's the velocity of the object? Right here and right here. 0. Horizontal lines on position versus time graphs, while yes, they are constant velocity, they are constant velocity of 0, meaning that they are at rest or not moving. Okay? Good so far? All right, picture number 2. 30 seconds. Talk about what's next to you. Go. Make sure we're using vocab terms, right? All right, let's discuss. So, what's happening at the beginning of this graph? Okay, it's moving with a constant velocity, right? Second part of the graph, what happens? Stops. Third part of the graph, what happens? Moving at a constant velocity, but it's slower than the first constant velocity, right? So, steep lines are an object moving with a high speed. Shallow lines are objects moving with a slow speed. Notice that I changed a little bit of the wording. There's a reason why. We'll see that in the next picture. Okay? So steep lines, an object moving with high speeds. Shallow lines, objects moving with slow speeds. All right. Good? Picture number 3, 30 seconds. Talk with the person next to you. Go. All right, let's discuss. This graph starts off how? At rest. Then what happens? It goes backwards. What do we see about the slope in the second portion of this graph? It is a negative slope. Is it constant? Yes. It's moving with a constant velocity, but it is a constant negative velocity, right? Negative velocity, Julia, what does the negative on the velocity tell us? It gives us more generally it gives us the direction, right? If we have a negative velocity, that means it's moving in the negative direction. That doesn't necessarily mean that it's fast or slow. It's just moving in the opposite direction. The previous picture, right? Steep slope, shallow slope, I gave you speeds. We can have a very steep negative velocity, right? Or a very steep negative slope, right? That means it's moving fast, just in the negative direction, right? So, negative slope means an object is moving in the negative direction, and therefore it will have a negative velocity. It only tells you which way it's going, not how fast it's going. Okay? Good there. All right. Last picture for this section. 30 seconds. Discuss. Go. So to wrap this section up, I would like a volunteer who would be willing to open themselves up to public criticism. Anybody? Anybody? Tyler did shoot his hand up pretty fast, all right? So, Tyler, stand up for me here. Okay, come around this way. All right, so, Tyler, if you're willing to, after you hear the whole detail of this, right, would you be willing to demonstrate this graph with a physical motion for us? Sure. Okay, so, we'll have the motion occur in this space between the front desk and the front row, okay? I will call this the reference point. So okay? Like the start? This is, no. Or like halfway. I'll leave that up to you, okay? So, I'm going to give you a countdown. So guys, 3, 2, 1, go. And then I want you to move how you would move to make this graph, okay? Yeah. All right, so I will let you start wherever you want to start, okay? So go ahead and
Am I allowed to move this or out?
Leave that there. I want you to move in relation to it, okay?
I want to call that halfway, like halfway up. So it's like...
So now, let's do this, okay? So if this is the reference point, right? We said that an object that is at the reference point has a position of what? 0, right? Does that make sense?
Yeah.
Okay, is that going to change where you might start?
Yeah.
Okay.
Definitely.
All right. Are you ready?
Yeah.
3, 2, 1, go.
So like does it go anywhere for a second, and then it goes like this far forward, and then goes back, and then goes forward again.
And then at the end, okay. All right, so hold on just right there for a second, okay? All right, so some good things, some things we might need to change. Okay? Grace, go ahead.
I don't know if this is right or not, but if you started at the reference point 0 when you start in the counter,
Okay, so if the reference point is 0, right, this didn't actually start at the reference point. So instead of starting at the cup, maybe you start like, yeah, at the monitor, okay? When you went backward, what else? Anything else? Anything else you want me to criticize? We can also compliment as well, so go ahead. Okay, he maybe needs to go a little bit faster, right? Although we don't really have any numbers on this graph, so it's hard for us to say exactly how fast this is. Okay, Andrew, go ahead. That's good. That is a compliment, and I appreciate that. And I'm sure Tyler appreciates it too. You know, so. There's maybe one other thing. There's maybe one other thing that I thought he did well in his movement. Okay, go ahead. You didn't, and when you were talking, I think I heard you say this. You don't go all the way back to where you started, right? This turnaround point right here is above where you started. So yeah, you wouldn't go all the way back to where you started, right? And where you finished, you're farther than where you turned around the first time. Okay? Good there. Okay? Good job. All right. One last thing I want to say on this graph, okay? Here, let me grab this picture, okay? Because I want to put it here so I can draw on it. Okay, here. Okay, all right, so. Okay? 2 lines there. And then, okay, I want you to look at yellow as a group and pink as a group, okay? The pink, one of the yellow lines and one of the pink lines are the same line, but I want you guys get what I'm trying to say? Okay. All right, so I want you to compare and contrast speed and velocity for the yellow pair and for the pink pair. Compare and contrast speed and velocity for the yellow pair and the pink pair. Discuss. Go. Yeah, the 2 yellow lines. Compare and contrast those, and then separately compare and contrast the 2 pink lines. Yeah, compare the 2 yellow lines first, and then compare the 2 pink lines. Yeah, compare yellow to yellow. And then compare pink to pink. Okay, let's discuss. All right, let's compare yellow to yellow first. And I asked you to consider 2 things, speed and velocity. First, mathematically, what does it look like is true of these 2 yellow lines that I've highlighted?
That yellow line has a higher slope.
You think? If that's what it looks like to you, that's fine, okay? I say to me, those 2 yellow lines look parallel, okay? What do we know is true about 2 parallel lines? Same slope. So what would we say about the 2 yellow lines if we're comparing their speed and velocity? If they have the same slope, they have the same velocity, right? And if they have the same velocity, they got to have the same speed. Okay? However, what about the 2 pink lines? looks pretty much to me like those are opposite slopes, right? Meaning what? If they have opposite slopes, that means that the number is the same, right? But one's positive and one's negative. What would that mean about their speed? It's the same speed because it's only telling us how fast. But do they have the same velocity? No, because one is going one way and one is going the other way. Does that make sense? Right? So yellow, same speed and same velocity because they're parallel. But pink has the same speed but different velocities because one's positive and one's negative. Good there. All right. Flip it over onto the back side. And let's take a look at this. 30 seconds. Describe the motion of this object. Go.
What is that? What is that? Yeah. So like it gradually gets faster.
What does that mean? That is, Laura, that's true, but that tells us something about this object. All right, let's discuss. Okay, let's discuss. All right, let's discuss. Laura, the first thing that you said when I was walking by is what about this graph right here? It gradually gets a steeper and steeper slope. That's true. Then I told you, yes, that's true, but physically that means something. What does that mean is happening to this object? Did you figure that out? It's getting faster and faster and faster and faster and faster. Okay? Is this a constant velocity? Not a straight line. Okay? This is a changing velocity. Laura, specifically, the velocity is getting faster. Okay? This is an example of the third question that we talk about when we talk about mechanics. So if you have your other outline, here's where we're going to transition to the last page. Okay? So, 4 questions, right? First question, where is the object? We call that position. Second question, what's the object doing now? That's velocity. The third question being, what will the object be doing in the future? Is it changing what it's doing? Right? And Laura, we saw on that graph, that object is changing what it's doing, right? It's getting faster and faster and faster. We refer to that change as acceleration. Acceleration is the rate at which velocity changes. Or, how much is the velocity of that object changing? We talked about that if we describe something as a rate, anything that we describe as a rate means what? We said that if we describe something as a rate, there is one factor that we always must include. That factor is time, right? A rate is always something over time, right? So, the acceleration is the change in velocity divided by the time over which that change occurs. Mathematically, it looks like this. Delta V over T. All right, so a couple of things about this. First, the delta represents what? Change. We said in order to calculate the change in something, we need to know what? In order to calculate the change in anything, what do we need to know? How it starts and where it finishes, right? So we can take this equation and we can also write it so it looks like this. Mathematically, those are exactly the same thing. One's just more detailed than the other. Okay? Now, units though, if we do a velocity minus a velocity, we should still end up with meters per second. But now we have to divide that number by what? So the unit for acceleration is meters per second, which is obviously a complex fraction. Okay? It describes how much the velocity changes every second. However, you will almost never see that unit written that way. It's kind of complex, right? Not kind of, it's a complex fraction. This complex fraction gets simplified to look like this. Meters over seconds squared. While mathematically those two fractions are equivalent, meters over seconds squared can be misleading. If I say that a runner runs 100 meters in 12.5 seconds, you can't take 100 and divide it by 12.5 squared to get the acceleration, right? Even though unit-wise that would come out the same. That's not what this unit means. This unit is a simplification of this unit, meters per second per second. It tells how much the velocity changes. Okay? Good there? We didn't quite get to the end. I'll spend 5 minutes at the beginning of class on Monday talking about the last part of that outline, and then you will have the rest of the time to work on your lab. Okay? Oh! Monday and Tuesday of this week. Hey, hold on. On the calendar, Monday and Tuesday of this week. If we go here, not look at this week's weather, but if we go here, Monday and Tuesday of this week, there was some homework on the calendar. We have now finished all of that information. So if you haven't done that homework before, now you'll have all the stuff that you need to do it. Might be a good idea going into your quiz on Tuesday. Have a good weekend, everybody. See you guys on Monday.